5.3, solving trigonometric equations. This is Trigo, the alligator. Ha! Trig equations. This is something I've shown you before. In fact, I had you do something like this, where you did sine inverse 1/2, and you said, well, this has to equal x. And remembering that sine has the restriction, inverse sine has a restriction of negative pi over 2 to pi over 2. We're looking for a positive 1/2. That's right here, and that's pi over 6. So x equals pi over 6. That's if we're doing inverse sine. It's if it started like this. But if it starts like this, it's technically every single value that's possible, starting with pi over 6, and it's every circle away from that, because on the unit circle, if we're starting at 1/2 or pi over 6 for our inverse sine, then it's going to go around, and it's still back there. In fact, this gives us the idea of arc sine. This is the difference between the two values. Arc sine 1/2 is not pi over 6. In fact, it's pi over 6 plus 2n pi for integer values of the circle. There's also 5 pi over 6, because at 5 pi over 6 we are just over here, which is also sine 1/2. So it's just the two different values and adding and subtracting a circle. This little image right here is explaining it from a graphical perspective, knowing that pi over 6 is right here, and there is a period of 2 pi away between those values, and 5 pi over 6 to here is 5 pi over is 2 pi away from it, and 2 pi backwards this way. So these are the general solutions we're going to use for solving this trig equation. All right, with that we can do things like, this is just another perspective from the unit circle like I drew on the other sheet. Say we have something like this. Well, we can't solve for x until we first get all the trig functions to one side and, if possible, into one trig function value. So I see that sine is over here with some square root of 2 stuff, so I'm going to get this and move it over there. So let's go ahead and do that. Square root of 2 is equal to, if I subtract sine from both sides, I get negative 2 sine x. Then if I divide by negative 2, I get that sine x is equal to negative root 2 over 2. I think it's more helpful to think about this from an arc sine perspective rather than an inverse sine. Inverse sine being the restriction here, but arc sine is any possible angle. So that means the entire unit circle is possible and any coterminal angle to a unit circle angle. Yes, that was a lot of words. Sine is negative in the third and fourth quadrants. Within the first circle between 0 and 2 pi, 0 being the first value and 2 pi being the ending without actually getting to 2 pi, the values are the quarter ones. So this is 5 pi over 4 and 7 pi over 4. Now, I just take those two values and it's any circle away from them. So, general solution for this would be x equals 5 pi over 4 plus 2n pi, n being an integer, and x equals 7 pi over 4 plus 2n pi. All right, let's do the next one. We have to preferably get this down to a tan x. So what I'm going to do, since it's squared and it's by itself, there is no singular tan x, I'm going to solve for the tan squared x. So I add 1 to both sides and divide by 3. Now, in this case, we can also divide by, square root it, but when you apply a square root to a problem, we have to do plus or minus. Well, there's a cleaner way to write this. Now, you're probably thinking, well, which coordinate is this on the unit circle? Or at least hopefully you are. Let's do our first quadrant just to reason this out. Now, we have this coordinate or this one with the square root of 3 over 2, 1/2. I'm just thinking of the unit circle here. 1/2 and square root of 3 over 2. It's either of those values. Remembering that tan is defined from the unit circle. Tan theta is defined by the y divided by the x. So if I do the pi over 6 one, it's this one, which becomes 1/2 times 2 divided by root 3, which becomes 1 divided by root 3, which we saw is this one here. So it's not this coordinate here, it's this one. And this is the pi over 6. Notice it's the y divided by the x, so the y always has to be a half. Notice we have a plus or minus, so we're these coordinates here. Notice the reference angle in each of these values is pi over 6. So I would list these out like this. Now, there are 4 angles, but instead of being 2n pi, we actually have a shortcut by just saying pi. So let me say it this way. Our first one is pi over 6. Notice to get from pi over 6 to 7 pi over 6, we would add a pi to it. And then if we add pi to 7 pi over 6, we're back to the coterminal angle to pi over 6. So instead of adding 2n pi, we're going to add n pi. Continuing on, this one over here is 5 pi over 6. And we're going to add n pi to that as well, because it's every half circle away to the other angle, which is 11 pi over 6. Alrighty, that is our general solution. Going to the next one. We've got this cotan, cosine business, and cotan. Well, before we can analyze where this is, or where all the values are, we need to get it down to one trig function if possible. So notice we have a one trig function over here, but since I know this is equal because I'm solving it, then I can group them all to one side. So I'm going to go ahead and group all this and solve for 0. So I've got cotan x, cosine squared x, and then minus 2 cotan x. Let's take this and see if we can go somewhere with it. All right, this might be a bad move as far as making it messier, but we're just going to go ahead and start it out and continue. All right, notice both of these have a cotan. Now, in this case, you might be tempted to try to get this cosine squared turned into sine squared, but we don't need to, because this is considered a factor and this is a factor, and they're set equal to 0. Well, if either factor equals 0, then the whole thing is 0. So what we do is set this equal to 0 and this equal to 0. So I do that here. All right, then we just solve each once. Now, personally, when I see cotan x, I like to turn it into the quotient formula, which is cosine x over sine x. Now, there's nothing that sine can be that can make this whole output 0. So I just take the numerator, cosine x, and set it equal to 0, because if cosine is 0, the whole thing is 0. And now I'm looking for the values where this is actually 0. I like to think of the unit circle when doing these things. Cosine is the x values on the unit circle. We're at pi over 2 and negative pi over 2, and every coterminal angle away from that. Pi over 2, negative pi over 2, and every other angle with those. So it's pi over 2 plus n pi, every half circle away from it. That's our first solution. Then that goes with the cotan x. I'm going to come over here and add 2 to both sides. Then I'm going to square root. And remember to apply plus or minus. Now, where does cosine x equal plus or minus the square root of 2? Now, here we have a problem, because plus or minus the square root of 2 is the same thing as plus or minus 1.41 blah blah blah. Remember that cosine can never be higher than 1 nor less than negative 1. So this is outside the range of cosine x and yields no solutions. So the only general solution that we have is this one. Okay, we got some of the quadratic type. You're just going to have to factor it, treating sine just like it's a variable x, or secant just like it's a variable, and then go from there. Like, let's say we have 2 sine squared x minus 1 equal to 0. And we need to factor this and solve. I'm only going to do this algebraically, though you could do this graphically and find out where this function equals 0. Sorry for the bell. All right, so I'm going to do this by factoring. Some of you might find this useful to do the use substitution. Personally, I think it's more obnoxious than necessary. Take the 2 and the negative 1 and multiply them. Take the negative 1 right here and write it beneath it. We're asking what two numbers multiply to get negative 2 and add to get negative 1. They're going to add to get negative 1, multiply to get negative 2. If they multiply to get a negative and they add to get a negative, then the bigger one must be negative, and one of them has to be positive. So negative 2 and 1. So what I'm going to do is I'm going to split this negative sine x into the negative 2 sine x and the 1 sine x. We still have the 2 sine squared x, and then we still have the minus 2 sine x, and then plus sine x, because that goes with the 1, and then I still have the minus 1 equal to 0. Now I just factor by grouping. So we have 2 and sine x in these two terms. I'm left with sine x minus 1, And then I have sine x minus 1 here, but you can always factor out a 1. Alright, notice these two are the same, which they will be if this works. So then we have sine x minus 1 times 2 sine x plus 1. And this is equal to 0. Now we just set each of the factors equal to 0 and solve. So we have sine x minus 1 equal to 0 and 2 sine x plus 1 equal to 0. And we just solve each one. Sine x equal to 1. I like to do this from the unit circle. Sine is the y value. Sine is equal to 1 here and here. Notice that's pi over 2 and every half circle away from it. Then let's do the other one. Notice this is sine x equal to negative 1/2. Where is it equal to negative 1/2 on the unit circle? Negative 1/2 is here because sine goes with the y value, and here. This first angle is 7 pi over 6. And the next angle is 11 pi over 6. 11 pi over 6 is what I meant to write. Now, in this case, there's no shortcut way to relate the two of these because you can't add a certain number every single time. So we're going to separate these two and say 2n pi, meaning adding circles to them. Whoops, 2n pi. Alright? Except it would be good if I read the directions, because the directions say that it's got to go between 0 and 2 pi. 0 and 2 pi, not the general solution. So I just truncate this little general part, and you have no need for half circles. It's just between 0 and 2 pi. So these three are the answers. That's it for this video.